Here for the 6th International Conference on PI Mathematical Physics and its Applications. Technically speaking, we are in the Abacus lab, which is the home of our newest supercomputer called Abacus. So, welcome to Mexico and Mexico City. I hope that you enjoy your visit and the conference. Now, Branko is going to say some words.
Okay, dear colleagues and friends, I was this morning almost frozen, so now I'm unfrozen, so I think that I can say a few words. It's very nice to see all of you here in this very nice place and very interesting for us, even organized by Lucio and this local organizing committee. I would like to recall you some points related to this series of conferences. This one is the 6th. We started with this series of conferences on 2003. The first conference was in Moscow, in the State of Mathematical Institute. And then the second one was in Belgrade, in Serbia. Third one was in Belarus. And then next one was in Germany. Then again in Serbia in 2015. We were also there. Some other people also from this audience. And then Wilson proposed to have the 6th one, next one, to have it here. And I think that it is very successful. It will be also successful. Yeah. And so I think that during this conference we'll discuss where will be next one. I think that it should be in the future every 2 years. We should continue with these conferences. It should be every 2 years in the future. As you know, we have also a journal related to this subject. It's called the Periodic Numbers Ultrametric Analysis and Applications. And I cordially invite all of you to send your paper related to your talk here, and not only to the talk you present here, to send it to this journal and we will publish it. Within 3 months, maybe, we have 4 numbers a year. Okay, so I wish you to have a very active and very useful participation in this conference. Thank you.
It's a pleasure to announce the opening talk by Debashis Ghoshal and Ultrametric group towards Berry-Keating.
I'd like to begin by thanking the organizers for inviting me to give this talk. I'm probably the person who's come the farthest for this, but
I'm trying to get off the line. It's okay, go
ahead. I have the advantage of having come a few days in advance, so many of you have just traveled and tired, so Wilson asked me to give the first talk. It's a pleasure and an honor. I was actually looking forward to meeting Professor Peter Freund, but he could not make it, so it has been shifted and I get to give the first talk. It's a real pleasure to be in Mexico, a country which is beautiful and reminds me of my own in many ways. But those of you who have been to India will probably see the similarity with the trees, the fruits and flowers that you see, and also generally what, if I may be permitted to use the word, organized chaos, which we both share in the two countries. I'd also like to thank Wilson especially for making too many requests and asking too many questions, which he very indulgently obliged. So let me start with the talk. So I will talk about an ultrametric route towards Berry-Keating Hamiltonian. I made a small change from the title that I had given, which was ultrametric route to Berry-Keating, but we still haven't figured out all the details. There are some loose ends that we need to tie up. So I have changed it to towards so that I'm on safe grounds. It's not quite finished. So this talk is based on some ongoing work with my young collaborators, Arna Chattopadhyay, Parikshit Datta and Sumakar Datta. And as I already said that there are many loose ends, so I will mention those as and when we reach them. Roughly speaking, this talk is in 4 parts. I'll give a brief introduction and motivation, and then I'll discuss or recall some properties of unitary matrix model and its space-based description, and then I'll go to brief review of some work that my collaborators have already done on unitary matrix model from the symmetric zeta function, and then we'll, in the last part, I'll talk about what we are trying to do by constructing a unitary matrix model from the local zeta function and trying to put all the information for different primes together to describe the Riemann zeta function. So as you can see, this talk is related to the Riemann zeta function, which, although not directly related to periodic numbers, have close connection with periodics, and we use, maybe not very centrally, but marginally, the properties of periodic numbers. I'm actually not very conversant on periodic numbers because this is only my part-time interest. I'm mainly a high-energy physicist, not a mathematician. So let's start with the Riemann zeta function and recall some properties. This function has been a very intriguing and fascinating object ever since Riemann made his famous conjectures about the zeros of this function. The function was actually introduced by Euler as an infinite sum over integers, but as a function of this s, which is the power of the integer, and this is well defined for positive values of s greater than 1, integer values of s greater than 1. Euler also noticed that the same sum can be written as an infinite product over the primes, and that is the most interesting property of this function. This is a very straightforward identity to express it in these 2 ways. And after this was defined, it was extended to real values of s, still s greater than 1 by Chebyshev, and finally analytically continued over the entire complex plane as a meromorphic function by Riemann. Riemann studied this quite extensively and found that this satisfies a reflection identity which relates the value of zeta at the point s to the value at point 1 minus s by some factors which are dependent on s, gamma functions and sine functions. This function has a simple pole at s is equal to 1 and has zeros which are at all negative even integers. But that's well defined, very patterned zeros. These are called the trivial zeros of the zeta function. More interestingly, it has non-trivial zeros, which Riemann conjectured that they all lie on the critical line. Vn s is equal to half, or in other words, s is a complex number, half plus I times imaginary unit times Tm. This are called gamma in this talk, and Tm is purely real. This is the famous Riemann hypothesis, and associated with the zeta function, we can define the psi function by multiplying some factors of s and gamma function, which kills the trivial zeros at the negative even integers. And this is an entire function. There is no pole also. The pole is also taken by putting this factor, which has an exact reflection symmetry about the axis s equal to real s is equal to half. And the function has zeros only at the non-trivial zeros of the original zeta function at gamma n. So sometimes people work with the psi function. It's equivalent. What is interesting about the non-trivial zeros is that their distribution is not known. We don't know exactly where the next zero is going to be. All we know is that if there is a zero at half plus I times Tm, there is one at half minus I times Tm. So they're symmetric about the real axis. But other than that, the distribution is an unknown question. And whatever it is, it's related to the distribution of the primes because of the product form of the zeta function for some range of the variable in which it is defined. So it's known to the mathematicians that if we can find the distribution of the zeros, then we can relate it to the distribution of the primes, and we'll know how the primes are distributed, which is an open problem, and conversely. So both these problems are unsolved problems. But somehow it's probably believed that the distribution of zeros is going to be easier to find rather than the distribution of the primes. At least that's what one would expect from the perspective of theoretical physics, ever since Kodia and possibly Hilbert made the conjecture that these zeros could be realized as eigenvalues of some self-adjoint operator. We are familiar in quantum mechanics with Hamiltonian operators whose eigenvalues are energies, which are real because the Hamiltonian is the Hermitian operator for physical systems. But one can generalize and talk about Hamiltonian operators whose eigenvalues need not be real, but they are self-adjoint operators, and in this case it's also unbounded because the zeros are on both sides of the real axis. There is some support for this conjecture already from starting with the work of Montgomery in 1973, who computed the 2-point correlation function of the Riemann zeros. And he was visiting the Institute for Advanced Study in Princeton when Dyson pointed out that this 2-point function has the same behavior as the 2-point correlation function of the eigenvalues of Hermitian matrix model. Random ensemble of Hermitian matrix model, which Dyson studied very extensively, introduced by Wigler, and a lot of work was done by Dyson in this field. This was numerically confirmed by Odrisco, who at that point probably computed 10 to the power 12 zeros of the Riemann zeta function, but by now he and others have computed this to even larger numbers. And using these numerical values, one can compute the 2-point function of the Riemann zeros. And he showed that if you take different regions of these distributions, then you find this conjecture is confirmed. And the larger in value of the absolute value of the zeta function that you, the zero of the zeta function that you go, the better is the match with the theoretical formula. Since then, this property has been checked for not just 2-point functions, but by higher point correlation functions of the zeros by various authors, in particular by Rubnik and Sarnak, who also extended it for the zeros of generalizations of Riemann zeta function called the Dirichlet L functions, which are defined as an Euler sum over integers with an additional factors of the character of n. This is some well-defined function of integers, and this also has a product form. The Riemann zeta function turns out to be a special case where the character is just 1 for all integers, and these are more general class of functions which all are conjectured to have the same property, that their non-trivial zeros along the real s is equal to half axis. So, to study the conjecture of Euler, various people have tried many different approaches. I'm not familiar with all of them, and I'm just learning this subject, started a few months ago. So there is a vast literature, and every day almost you can find new approaches people have tried. One of the approaches is due to Michael Berry and Jonathan Keating, who proposed that one can find a Hamiltonian whose zeros, whose eigenvalues will coincide with the zeros of the zeta function. In fact, it's a very simple Hamiltonian. It's the quantization of the classical Hamiltonian x times p, which one can write symmetrically in quantum mechanics as xp plus px, and then it comes out to be just the addition operator plus shifted by a constant. The motivation for Berry and Keating to propose this as the Hamiltonian comes from comparing the fluctuating part of the prime distribution function, which is already introduced by Riemann, and the Gutzwiller trace formula, which relates the fluctuating part of the energy eigenvalues and the time period of a classically chaotic dynamical system. So there is a problem in studying quantum chaos, in which it's not clear how to really describe chaos in a quantum system. So the proposal is to look at the eigenvalue distribution of the Hamiltonian, and a chaotic classical system has the property that trajectories with fairly close by initial conditions diverge as a function of time, and the solutions are very sensitive to the initial conditions. So this property, there is no analog in quantum system because there is no notion of trajectories. So one looks at the spectrum, and in the spectrum one can see traces of chaos wherever there is a classical counterpart of the quantum system. And Gutzwiller related the distribution of the eigenvalues to the time period of classically closed trajectories, and in particular for chaotic systems and non-chaotic systems, the distribution is, the relation is very different, and he showed that in particular for chaotic system how this relation is supposed to be. And if you look at the relation, it is very reminiscent of the prime distribution function. At least the fluctuating part of both is like the prime distribution. There is an average, and then over that the fluctuation. So the analogy is that Riemann zeros and their conjugates are the primes, and on this side the energy eigenvalues are the ones that correspond to the Riemann zeros, and the periods are the ones that correspond to primes. So given any periodic orbit, it's possible to have a primitive orbit, which is in which it just traced once, and then also multiple tracing of the same orbits which are not to be counted separately. So that's the analog of primes and the integer powers of primes in this approach. There are some issues with the Berry and Keating's proposal. It's not clear what the Hilbert space is, and an XP Hamiltonian is not really classically chaotic. The spectrum is also continuous. It is in fact the XP Hamiltonian you can get by starting with the inverted harmonic oscillator and doing a canonical transformation, defining x plus p and x minus p of the inverted harmonic oscillator as the new x and new p, and then that's the Hamiltonian, XP Hamiltonian. So therefore the spectrum is continuous. So to remedy this, Berry-Keating made some proposal, that is to put some lower bound on x and p, and many other people have tried some modifications to make this into a chaotic system, but this, to the extent that I know, there is still not a very clear resolution of whether this is the right approach or not. A very related approach is taken by Alan Kohn through non-commutative geometry, but these papers are very mathematical and I didn't really understand much of it. Some summary at other places seem to suggest a close connection between Kohn's work and Berry-Keating's work, but it's still probably not totally resolved, so there are still open questions in this language. What we want to do is to use matrix model description, so, the same kind of matrix model that Dyson studied, and recently there has been a phase-space description of unitary matrix models, and once you have a phase-space description, one can try to infer about a classical Hamiltonian, and then of course try to see how to quantize the classical Hamiltonian. So in particular we'll be talking about unitary matrix model. So this is the work of my, partly the work of my collaborators, there are of course earlier works. So I'll take a few minutes to summarize and review what is known here. So what one is studying is an ensemble of random matrices which are drawn from some probability distribution of matrices given to you, and from there we want to study what is the eigenvalues of, what are the eigenvalues of these matrices, and in particular we want to study the distribution of the eigenvalues of these matrices. So if we are talking about unitary matrices, then the eigenvalues all are unimodular, so they are the form e to the power I theta, so theta is the coordinate that I am using here, and a density function can be defined as just at the position of the eigenvalue, there is a delta function. Starting with this, we have a distribution function on the unit circle, function of theta. If you want to study eigenvalues which are on, say, some particular curve on the complex plane, in this case the curve is parallel to the imaginary axis, then one can use a conformal map to bring this curve to the circle, the unit circle, and then the zeros which are on this line will be mapped to the points on the unit circle, and this map is of course explicitly known. So it's equivalent studying a system like this whose eigenvalues are on some fixed curve, or eigenvalues of a unitary matrix model which are all on the unit circle. So it's sufficient to start with the unit circle model, and among the unitary matrix models, the class of model is called the one placket model, which have the following form of the probability distribution. The measure is given by this factor exponential of minus beta n by n tracing to the power n plus tracing dagger to the power n. It's called the one placket model because this generalizes the one that comes from studying lattice gauge theory, where we have minus beta times trace u, which describes in the continuum limit the Young-Mills action, and beta behaves like the finite temperature or finite inverse temperature of the system. And here it is generalized by putting all powers of n, and there is a conventional factors of n which is taken out. This n is the size of the matrix, n by n is the size of the matrix. And then we integrate this over all matrices to define the partition function. This measure is defined as the product over all the entries of the matrices. Since the action is symmetric under transformation, it does not change, it's invariant under unitary transformations. Instead of working with the matrix measure like this, it is more tractable to go to the eigenvalues of the matrices ui, e to the power I theta I, and write this as an integral over the eigenvalues d theta I. Once we do that, there is a Jacobian factor because we get rid of the angular variables, and we can write this as an effective action of these thetas. This term comes from what we have from this action, and this extra term which comes from the Jacobian factor. This comes from the van der Waals determinant that relates the two measures. So S effective is cos of n theta I plus log of sine square theta I minus theta I. This term actually corresponds to a Coulomb repulsion term on the unit circle. So it's the eigenvalues behave like fermions which repel each other. They don't want to be clustered close together, and this term in the potential is the indication for that. So in the large N limit, the problem simplifies. That's when one knows how to solve this problem. In the large N limit, the index I divided by n is replaced by a continuum variable x which takes values between 0 and 1, and the eigenvalues theta I go to theta x. And theta, the action S effective, this should have been S effective again, S effective becomes the sum over I becomes an integral over x, and we have the same form in the continuum form, but now this can be solved. The saddle point for this action is given by this equation, which determines the density function rho of theta, and this will determine the density of the density distribution of the eigenvalues, and the potential derivative of the potential is this term. So the density and the potential are related by this saddle point equation. This is the equation of motion. So given the parameters beta n of the matrix model, one can determine this density function, or vice versa. Given rho theta, one can find beta n, and that is through the resolvent of this matrices, case of 1 by 1 minus z times u, and this resolvent is a very useful function. If we Taylor expand the resolvent, then one can relate the betas almost directly from the Taylor expansion of this resolvent. There is a discontinuity, so resolvent for mod z less than 1 and mod z greater than 1 behave somewhat differently, and this is the relation between, this is the exact relation between rho theta and the discriminant. So this is the real part of the discriminant minus 1, twice real part of the discriminant minus 1 is the rho theta, and there is also this v prime, the potential can also be related to the discriminant, one can determine the potential from the discriminant. So given, if we want to describe a particular distribution of densities of eigenvalues, then we can manufacture a matrix model for which the eigenvalues will be exactly what we want it to be. So the partition function can alternatively be expanded in terms of irreducible representations of the underlying group, which is un in this case. So it's a sum over the characters of the irreducible representations R times some factors. I haven't written the expressions because they are a little long and difficult to fit in small size transparencies, but these are well known, these are completely known factors which depend on these parameters beta, but also a set of numbers k1, k2, k3, etc. And these are nothing but the well associated with to un, one can write Sk, the permutation group of various sizes k, which satisfy n times kn. So these numbers kn are these kn's, and n times kn is k. So the character of the conjugacy classes ck make an appearance in this expansion formula. These things are known for quite a long time and was extensively studied in the, at least in the theoretical language physics literature. There's a very influential paper by Michael Douglas who studied this distribution in in terms of these representations. And what leads to this formula is first an expansion in terms of the representations, and then using the fact that one can write trace of u to the power n and powers of them when we expand the exponential. These are the kind of terms that you get. These being class functions can be expanded in terms of the characters with known coefficients, and the fact that the trace of u in different representations are orthogonal to each other when integrated over u. That leads to this formula. But alternatively, we know that irreducible representations can be labeled by the number of boxes in the corresponding Young diagrams, and in the large n limit, one can replace the number of boxes hi's, which any representation will have a number of boxes in different rows. But in the large n limit, this I goes to a continuum variable x, and we have an integral over dhx and an effective action which involves hx and then also these variables p. In this description, we encounter a different density function, which is the density in terms of these boxes. So dx, which was the continuum variable, I really, so I by n becomes dx, and that is related to UH dH, when UH is the new density function in terms of the variable h. It turns out that this variable h is the conjugate momentum of the eigenvalues theta. So theta and h behave like conjugate variables. And when we write in terms of this parameter, in terms of this variable h, there are many delta function constraints actually, couple of delta function constraints. Not couple, 2 times infinity number of delta function constraints that appear in the expression for the partition function. And these delta function constraints can be written in terms of auxiliary variables as Lagrange multipliers. And a priori, these auxiliary variables are just introduced to take care of the delta function constraints. But it turns out that these auxiliary variables are nothing but the original eigenvalues when we write the matrix model in the eigenvalue expansion. So when we do that, we have the expression of the partition function not just as a sum over representations, but as a double sum over eigenvalues as well as representations. So this is like a phase-space description of the partition function, which is over summing over theta as well as h. And in terms of a density function omega, capital Omega, which depends on both the variables, and it is such that if we integrate out the h variables, then we get the density function rho of the eigenvalues, and if we integrate out the theta variables, then we get the density function h of the boxes. This phase-space description obviously can lead to a Hamiltonian, at least a classical Hamiltonian, and then one can try to quantize this. The classical Hamiltonian arises because we are talking about the large n limit. So this is the general matrix model approach, and now Shubhankar, my collaborator Shubhankar and Parikshit, two of my collaborators, they first studied the unitary matrix model, these one placket models, and got these results that I described, and applied it to the symmetric zeta function. So first, the approach is that they map the zeros to the unit circle. Actually, what they do is not directly the zeros, but they not directly the zeta function, but they work with the log of the zeta function, and map the, when you take the log, then the zeros becomes branch points of the logarithms, and these are mapped to the unit circle, and they compare the density that you get from this distribution to the resolvent function, and from the resolvent function they determine the coefficients beta n that would describe a matrix. It turns out, very interestingly, that these coefficients are up to a constant. These coefficients are numbers which are called Lie numbers, because Lie, a mathematician who introduced these numbers in relation with the symmetric zeta function. So this can be expressed as derivatives of some function which is related to the symmetric zeta function, and they can be written also in terms of the zeros of the Riemann zeta function. One interesting property of the Lie numbers is that they are monotonically increasing with n, and some properties of Lie numbers are equivalent to the Riemann hypothesis. So if one knows these properties, one can prove these properties of the Lie numbers, then one can prove the Riemann hypothesis. So it's very interesting that the coefficients of the matrix model actually comes out to be in the form of Lie numbers. The density, the phase space density they obtain is pictorially like this. This is in the h theta plane. So the unit circle is somewhere here. The density is 1 in the shaded region and 0 otherwise, outside like this. And you see that there are spikes in the density function capital omega wherever there are eigenvalues, wherever there are zeros of the xi function. There are spikes in the density in the phase space. The prime power counting function Jx jumps by 1 by n at every to the power n. It's defined like this. This is the Heaviside theta function, x minus pn, summed over p and n both. This has a average contribution and a fluctuating contribution. And this fluctuating contribution turns out to be related to the number of boxes, this function h, which is the momentum in the matrix model description. So, in this way, they were able to describe a matrix model related to the xi function. There is no clear way of going to the Hamiltonian description in this approach. There are also some points here is that instead of working with the xi function directly, they work with the log of the xi functions, and that leads to some problems when we try to interpret the Hamiltonian. So instead of this, what we propose to study is to break this into components and apply, sort of look at the atoms of the zeta function, which are the local zeta function, and try to first construct a matrix model corresponding to the local zeta function, and then we'll try to put that information together. I think maybe I'm speaking a little fast. I'm going to probably finish early. Okay.
No problem.
So the local zeta function is, of course, well known to experts here, but there are probably some students, so let me go through the definition of it. It's basically each of the prime factors in the definition of the zeta function. So in the zeta function, we have product over 1 minus p to the power minus s inverse for all prime p, but for a fixed prime p, that's the zeta at the prime p. This function, of course, does not have any zeros, but it has equally spaced poles, which are all simple poles, at the value s is equal to 2 pi n by log 2 pi I by log p times n, where n is an integer. So therefore, they are all on the vertical line defined by real s is equal to 0. So by a conformal map, we can bring these poles on the unit circle, and then we can crack the matrix model machinery to write the resolvent as resolvent in terms of these poles. So this factor is taken because this is the derivative of this conformal map. It's for convenience. So this is the resolvent for mod z less than 1, and this is the resolvent for mod z greater than 1. So this, if we write it this way, it satisfies all the properties that one requires of the resolvent. Namely, that at 0 the resolvent should be 1, as mod z goes to infinity, the resolvent should go to 0, and the sum of the resolvent function for less than 1 plus greater than 1 with argument 1 by z should sum to 1. There is one caveat, and this is probably a technical issue which we have not been quite able to resolve, that the point S is equal to I plus or minus I infinity, which maps to Z is equal to plus 1, is a little problematic in the sense that there is an essential singularity, as you can see from here, there is an essential singularity of this resolvent function. And when we go to the density distribution, then what happens is that the density of any object is supposed to be positive every day, and it should sum to 1. When you sum the density over every circle, it should sum to 1. So these are the two properties we need of the density function. In this approach, what happens is that at z is equal to 1, which corresponds to s is equal to plus and minus I infinity, the density actually is like minus infinity with an amplitude which is that's negative with an amplitude which is infinity, and that is what helps in getting integral of rho is equal to 1. If we leave out the point equal to z is equal to 1, or equivalently s is equal to plus or minus I infinity, because that's strictly speaking not on the s plane, then we have positivity, but we lose the property that rho should integrate to 1. So that is one or the other problem we have to deal with. The problem comes from the fact that if we take the log of this function, then at each 0, in the previous approach they worked with the log of this function, at each 0, because of the branch cut, the log has a jump to the next Riemann sheet, and once you have traversed the entire circle, we have made an infinite number of jumps to compensate for that, to get a row which will sum to 1 and give a finite value after proper normalization. It has to make an infinite negative jump. That is the problem. And this is probably a technical problem. We can remove it by working with the log of the local zeta function instead of the local zeta function directly. But then we have a different problem that I will come to. Okay, so now, as is familiar to everyone here, this famous integral, that if we integrate this function over an open set in the periodic numbers, then the result is this. This is just this fact that all periodic numbers whose mod is less than, oh sorry, there's a typo here. This should be all numbers less than b to the power n. So this is the b to the power s. This is the well-known integral, and you see that this function appears in the resolvent. So we can write the resolvent using this integral. Then the resolvent itself is integral of a density over some subset of periodic numbers. So the resolvent gives rise to this part of the resolvent gives. Remember that this part of the resolvent 2r minus 1 is the density of the eigenvalues. So the density itself we are writing as an integral over another density function. So that suggests that we can define a phase space density, capital omega theta and h, function of theta and h, which is the density function that we find here. The problem is that this density is in the space of eigenvalues on one side, that's theta, but this h is only zp cross. So these are not ordinary numbers. So therefore, the phase space interpretation, what the phase space is not entirely clear. Whether we should think of it as real number times integer, in which the notion of the distance along the momentum direction is an ultrametric distance, or it is simply real numbers time an ultrametric space in the momentum direction. That whichever it is, seems to be suggestive of this particular phase space density. So it has a fairly simple form. And again, the problem of theta equal to 0 remains. There is an essential singularity there. So that technicality is still a caveat that we don't know how to resolve yet. What's more interesting is that this is the classical density function. Now, thanks to the work of Ghoshal, we know that p to the power minus n times alpha is the eigenvalue of the generalized Vladimirov derivative d alpha. This is defined as an integral kernel over the periodic numbers. This is familiar to the experts. Initially, he defined it for integer n, but later he also proved that this is the case for any complex number alpha. This is the eigenvalue of this derivative, so one can take the power, the kernel of the integral, in the definition of the kernel of the integral, alpha can be taken to be any complex number. And then we have the simple eigenvalue equation, d alpha on psi n is equal to p to the power minus n alpha psi n. These eigenfunctions, psi n, are periodic analogues of wavelets, and since Ghoshal studied these are called Ghoshal wavelets. And there are actually a few more, couple of more indices that I have omitted here. Psi n is labeled by 3 indices apart from n. There are 2 other indices, j and I forget what the other one is called.
Gamma.
Sorry?
Gamma.
Gamma. No, gamma I think is what we call n here. I think he calls gamma, j and...
Also translation stuff.
Translation corresponds to the... So this is the one that corresponds to scaling. There is one that corresponds to translation, and in the periodic case there is also a phase which is given by j from 0 to p minus 1. Okay. So that's a degenerate case which I have not written here explicitly, but that doesn't pose any problem. So this eigenfunctions space is spanned by this set of... there is a problem in the sense that the translation will give us infinite degeneracy, so we have to regularize that in while we want to define the trace, as we will define shortly. So the point is that this is the classical phase space density, which now we want to try to get to a quantum description. So we need an operator for which we want this density to come out. So we use these eigenfunctions and this particular operator to write that part as the fluctuating part really, as trace of this operator. This is the other factors which bundle neatly into the form of d of cot theta by 2. So this is trace of the Vladimirov operator raised to the power minus I cot theta by 2. So this gives the resolvent. Alternatively, we know that this fluctuating part has an expression in terms of the prime, this function which is related to the prime counting function, the j function, which jumps by, probably in the next slide, I'll go to that. So the energy eigenvalues are, as you can see from here, eigenvalues seem to be of the form cot theta by 2 n log p. These are the values of the classical Hamiltonian. It's not probably right to call them eigenvalues, but more like the classical energies. And this is clearly reminiscent of the Berry-Keating Hamiltonian of the form x times p, because this came from theta, so this is directly a function of theta, and this came from the momentum. So momentum is basically just n up to a factor of log p. So this is similar to the Berry-Keating Hamiltonian, but the difference is that the integer n only takes positive values. So the momentum is not negative and positive values, so we can't have it from translation, eigenvalues of translations, but they should rather be related to the scaling on the half line. So that should be the interpretation of the momentum operator in this case. So x and p are not a usual canonically conjugate pair. So when we write the Berry-Keating Hamiltonian as in the symmetrized form as xp plus px, it doesn't shift by a constant value, but rather it will shift by a p-dependent factor. The Hamiltonian, because we have used the Vladimirov derivative, the Hilbert space is quite clear. the Hilbert space is the one that is spanned by Kozyreg's wavelets, which are eigenfunctions of the Vladimir derivative. So we know which space these functions live in, and we know which operator we are dealing with. So coming to the matrix model now, remember that the parameters are given by the moments or the Laurent series expansion of the resolvent. So for the log of the psi function, the Lie numbers appeared. But this time, if we write for the local zeta function at prime p, the beta m zi to the power m 1 by m. So this is really the diagonal form of the action of the unitary matrix model. One term, there is another term which is given by U dagger. So this can be summed quite nicely in the form of log of this e to the 1 minus p to the power minus s divided by 1 minus p to the power minus 1 up to a constant factor. So we can explicitly write a matrix model. Modulo, of course, the caveat that I have described already in terms of having a technical problem at s is equal to plus minus I infinity. So now, in the remaining part, I will try to combine these results for all p. So we can write this matrix model for 1p, but it's not of much use. So let's try to write this for all p. So first, we'll redefine, we'll get rid of this factor of log p by absorbing it here, otherwise it just makes the formula messy. So we'll redefine betas by absorbing this factor of log p. And this basically amounts to, because the resolvent function was written in terms of, here it is, in terms of this d psi, dj, d psi, we are now redefining by log p, dj, p, d psi. So when jp is the function that jumps by 1 to the, by n at each power of prime p to the power n, this function will jump by log p by n for each power p to the power n. So this is also a well-known function. So we'll try to combine this for all p. So what we need to do is sum over all prime. The beta n's have to be summed over all prime, because we're just putting the primes all together to define the matrix model. The action is simply the sum of all the action for all the primes, all the prime factors, and the partition function is the product of e to the power minus beta times s. So the betas are simply summed. So that amounts to doing, that works out to be this. This factor is the same one that comes from each of the p's, and this is something that is related to the fact that we write this as a Laurent expansion. This is written in terms of beta variable, and the rest can be nicely packaged as a trace of capital psi n. And what is capital psi n? Capital psi n is nothing but the product of small psi n for each prime p. So we make a big Hilbert space by taking the product of direct product of all the individual Hilbert spaces for the prime factors p, and the wave functions are simply the product of those. So that's the capital psi. And this d operator, the bold d operator, is nothing but the sum of the p operators, the Vladimir derivative for each p. And when we apply it on this Hilbert space, on this wave function, it's the appropriate dp just goes and acts on the appropriate psi p. So this is the Vladimir operator at the pth place. This function jp is has an expansion, so this rather log times djp d psi has a known expression, which is in terms of the powers are the trivial zeros as well as the non-trivial zeros in this variable xi. In the rest of it, we will simply look at the non-trivial part of the zeros. These parts are straightforward, so there is nothing worrying in this part. So keeping only the non-trivial zeros, which are at the non-trivial zeros of a1 zeta, so that is this points gammas, the beta m's, one has to do this integral. If you go back here, in this expression, we have to do this integral, and concentrating only on the zeros that come from only the part that comes from the non-trivial zeros. So we have to do an integral to define the beta m's, which turn out to be in terms of d of log of xi, e to the power real gamma I log xi plus an imaginary part. The imaginary part is not important. The imaginary part of gamma I also appears there. This part, of course, is an oscillatory part, but this is the part that is of interest. See, log xi is a positive number, and this one, real gamma I times log xi, is appearing there. So this integral diverges since real of gamma I is positive, in fact it is half, so this term diverges. So mathematicians would probably worry, but we are physicists, at least I am a physicist, and my collaborators are physicists. We know we don't care about infinities. We are quite fond of infinities. We simply redefine things, call them renormalization, and plow on and leave it to the mathematicians to justify how to make sense of that. So instead of working with this, we'll say that we'll renormalize this and shift it by a factor mu. And if we shift it by an appropriate factor mu, that is mu is greater than real gamma, then of course this integral will be convergent and everything will be fine. So what do we need for gamma? What do we need from this shift? First of all, it has to be independent of I, because we want to shift everything by the same constant value mu. And the reflection symmetry of the zeta implies that as long as mu is greater than 1, this integral will be convergent, because real gamma is, of course, mod of real gamma is, of course, less than 1. So mu greater than 1 is good. But if Riemann hypothesis is true, then mu greater than half will be good. So then this will be well defined, and we can define a matrix model with this new renormalized values of betas. So this redefinition, as I said already in our approach, amounts to what as physicists we call renormalization. And there are two ways to view this renormalization. One is, of course, that the wave function is changed by absorbing this factor. Actually, sorry, this should have been p to the 1 minus mu by 2, so that we can symmetrically absorb it on the two sides in the trace. So either we renormalize the wave function, or in this case we are lucky because the special form of the Vladimirov operator and its eigenvalues in the form of exponential, that is p to the power minus n, we can, instead of renormalizing the wave function, we can renormalize the Hamiltonian, which is a much more desirable thing to do in this context. And this will lead to a one-parameter family of Hamiltonians, which we call h mu, which is shifting h by mu times p. It shifts by not by a constant but mu times p, because x and p do not have canonical commutation relation in this case. Alright, so this is basically the Hamiltonian that we would like to get at. But instead of one Hamiltonian, we have got one parameter family of Hamiltonian, and there are many open issues. Some I have already mentioned. The exact form of the Hamiltonian is not clear to us. Well, it's clear to us, but we know we've got some expression, but we are not sure that whether that is the one that will do the job. In this case, xp commutator is like xp commutator is some constant times p, okay? And that's part of the algebra that appears in the construction of the wavelets from the translation and scaling. So it's not unexpected, but how to make sense of this as a Hamiltonian in some classical space there's some things that we'd like to understand better. The other thing is this mu, which we can only restrict to a half-life, but it would be much more interesting if we can fix it to be the value we want it to be, namely half. Is it possible to do it? If we choose that value half, since real of gamma is half, there won't be any real part in that integral, it will be only imaginary integral, and presumably one can make sense of that. This also I mentioned briefly, the nature of the phase space, whether the phase space is an ultrametric space or it's a normal space with semi-ultrametric notion of distance along one of the directions or not, and what is the corresponding dynamical system, whether one can make proper sense of that or not is another open question. Then this I have mentioned more than once that we have some issues with s is equal to plus minus I infinity, or equivalently at z is equal to 0 or z is equal to 1 or theta is equal to 0. Okay. And this is presumably a technical issue. One can avoid it by working with log of zeta or log of local zeta rather than zeta. But the trace, definition of the trace becomes a little bit of a problem there, because we can't quite write this as, maybe somebody can help here. We can write this as psi n d to the power minus alpha psi n, but there will be an n dependent factor here. And then it's not quite, it doesn't have the interpretation of trace directly, and we can't absorb it by renormalization and still write it as a trace. So either we avoid the problem of the essential singularity and have problem with the trace, or we can write this nicely as a trace but have problem with the essential singularity at this specific point. So this is another thorny issue. And the other thing is that the effect of the gamma function, which is the trivial zeros, that has to be put in, and in the combination when we want to write this the full answer, but that should not really be a problem. In fact, that is desirable because the gamma function is really the analog of the p to infinity, or the real part of the non-Archimedean factors. So we need to put that to describe the full zeta function. So I did finish too early anyway. The other thing is that if this works, some ifs, of course, if this works, then it may be worthwhile trying to extend this for the directional functions as well. So I was asking Sergey yesterday whether one has any operator and functions for which the eigenvalues are not p to the power minus n alpha, but character p times p to the power minus n alpha. And if that is known, then this will go in exactly the same way, parallelly. So let me summarize. We have attempted to get to the Hamiltonian for the zeta function by starting with the local zeta function at the pth place. Okay. And for a specific p, this suggests a phase space picture with the hint of a Hamiltonian and a phase space and a classical dynamical system, which all needs to be understood better, but there is a hint, and quite a definite hint, modulo for some technical issues which needs resolving. And then finally we have attempted to combine this for all primes p, which has a divergence which needs to be regulated and renormalized. So this is still very much a work in progress. So I'd like to thank you for your attention.
Are there questions or comments?
Thank you very much. It's very interesting talk, especially because it is a relation between zeta function and physical something.
Which is also of interest to you who have seen papers.
Yeah, and I would like to say that in the 90s I considered adelic mechanics, and in particular adelic harmonic oscillator. Do you know about
I must admit that my knowledge of everything periodic is very limited, so I need to
it's
learn.
very interesting that when you consider one state for the adelic harmonic oscillator and take Melling transform for the spatial part, and then also for the momentum part of the Fourier transform, okay? And then Tate formula. One can take this function. This function in relation to the Riemann zeta function. So I think that one can also have some copies.
Yeah, I definitely look up. We are still trying to
Because we can
figure
have
out.
also this local function, so on, so on. So there are some similarities with this approach. So it means that one can take harmonic oscillator, consider it as a bed, one can also
Berry-Keating Hamiltonian is actually very closely related to the harmonic oscillator. It's the inverted harmonic oscillator and then a canonical transformation of that. Is it, if it is possible to do that with the idyllic harmonic oscillator, that could be one way of looking at it. Maybe we can talk about
Yeah,
it.
okay.
Are there more comments or questions?
A short one. In the beginning, when you introduced the Hamiltonian, let's say Berry-Keating Hamiltonian, you mentioned correlation, connection with the inverted harmonic oscillator. In which sense? Connection that they have the similar
The Hamiltonian is XP.
yeah, so with inverted harmonic oscillator, the relation is that they have the similar eigenvalues, or the spectra is similar. I didn't understand in which connection.
Yeah, in every
Exactly
sense.
that.
In every sense, yeah. You can get the wave functions from the wave functions of the inverted harmonic oscillator of this system. So it's actually the same system. You take the inverted harmonic oscillator and do a canonical transformation. Then that is this Hamiltonian extends P. So you know the wave functions there, you know the wave functions here. You have
I was just want it because I'm interested in that, but that's for after the talk. So just thank you very much.
Yes, I want to tell you something. Recently, this year we published an article in Algebra and Analysis, which is the journal of the Secretariado Institute in St. Petersburg. We studied the trace of adelic dot of the p-adic operators. In particular, we studied the trace from the Vladimir operators. The way in which you define the trace of the Vladimir operator doesn't make sense. You are working with the Vladimir operator as a densely defined operator in L2. It is not possible. You have to work with a smaller space. In my article, you can find all
please tell me. I mean, that's why I said that there are many loose ends that we need to tie up. But I think the general idea, there is probably something in it that is worth trying to straighten out.
The definition of the trace of a Vladimir operator as a densely defined operator is difficult. It's possible it doesn't make sense. It doesn't make sense.
Okay.
A couple of technical comments. Well, you work with a matrix model, and then you took the large and limit. Well, that naturally gives you a string theory. So the question is, have you tried to make a string theory model?
No.
Well, the other comment, when you draw in your...
We haven't yet understood this properly, so going beyond this, we haven't tried to.
When you draw in your phase space the part of when your function is 1 and 0, you get this kind of amoeba. You are interested in the asymptotic behavior. Well, that motivates to think in tropical geometry or log geometry. You know that you take the limit and you just see the asymptotics. You have a very combinatorial model of what is going on. I think that should be helpful.
Okay, maybe I'll ask you. We'll try to get the references and try to see.
Okay.
Thank you.
Okay, let's thank the speaker again. 5 minutes before the next talk.